Okay, that doesn't seem to work. Yeah, okay. Maybe I can do this. Ah, yeah, I can do this. Okay. All right, good morning, everyone. So first, maybe let's start with some questions, if you had any from yesterday. No, everything is good. So let us spend a little bit of time finishing discussing many-body localization, and then we'll talk about pre-thermalization and then see how much time we have left for other stuff. So, okay, so that's just what we saw yesterday, right? So we had introduced ETH ansatz for matrix elements. Right, so I will just flip through it to remind you a little bit, right? And this ansatz implies, right? It follows from this idea that in a thermalizing system, eigenstates are random vectors modulo some constraints imposed by energy conservation and locality, right? That's what fixed form. And right, so what we discussed is that this allows you to understand why quantum systems thermalize starting from an arbitrary physical initial state, right? And by physical I mean broadly something that I can prepare using local operations in a polynomial time and system size, right? So I would not allow myself to make a Schrödinger-Cat state of two eigenstates at very different energies, right? Because that would take me in general exponentially long time to resolve these eigenstates. But if I could do that, right, of course you would see weird thermalization dynamics, right? You would see macroscopic oscillations between these two states, and that's not something you can do in a large many-body system. Right, so central idea of ETH is ultimately very simple, that in ergodic quantum many-body systems, even individual excited eigenstates, they already look like thermal ensembles, right? Right, and then we had this very different class of systems which are many-body localized, right, which violate ETH, and an example, right? One example of a model that exhibits many-body localization we considered is this one here, right? So we have hopping, right? This is XX interaction in the spin language, ZZ interaction, and random field, and then we can tune the strength of disorder by changing the width of the distribution of the random field. And then the dynamical phase diagram, so because that's something, yesterday we talked mostly about the limit of strong disorder. So, at sufficiently strong disorder, we find many-body localization, right? And then as disorder is reduced, at some point we make a transition, right, into thermalizing regime where ETH would hold. And it's been, it's been a very interesting question, and still partially or even largely an open question, how this transition happens, right? And what is exactly the value of the critical disorder, for example, for this model. And so, and I'll discuss a little bit, underlying mechanism, how many-body localization gets destroyed as disorder is decreased, right? And what are the difficulties that you encounter towards building a convincing theory of it. But one thing I want to emphasize, right, what is interesting, so yesterday, as we discussed, if you think about Anderson localization, in one dimension, generally, all states are localized, even when disorder is very weak. So you see that interacting systems are not like that, right? So even in one dimension, you expect transition between many-body localized and thermal regime. So to try to gain some insight into this transition, so what was done early on is exactly studies hexagonalization studies of chains, let's say up to around 20, 25 spins. So here I'm showing some very early data from Pal and Hughes. And then what you can do, you can characterize level statistics, right? And we had this idea that in the thermalizing phase, in the ergodic phase, statistics would be Wigner-Dyson, and there is level repulsion. And what I'm plotting here is essentially some measure, right? Some one number averaged over levels and disorder realizations, which characterizes whether you're dealing with Wigner-Dyson statistics or, another option is to have no level repulsion. So when two levels come together, they don't feel each other. There isn't typically a matrix element to connect them. In that case, you're dealing with Poisson level statistics, right? There is nothing that prevents two levels from coming together. And generally you expect integrable systems, right? And many-body localized systems, as we discussed, are also integrable in some sense. There you expect, right? You expect Poisson level statistics. So this is measure. So essentially, this is a ratio. So it's just a proxy. So you look at levels, right, and then you look at triplets of levels, and R is the ratio of the smaller, right, smaller of these two level spacing to the larger one. Well, delta epsilon smaller, delta epsilon larger. Right, and this is one number, so you can compute it for Wigner-Dyson or Poisson, and that's just a proxy, right? Proxy to see. Because advantage of this is that this allows you to get rid of non-uniform density of states. Yeah. Right, and here, in this plot done for this exact model, for the spin model, as a function of disorder strength. So you see how this crossover from Wigner-Dyson and level repulsion happens to Poisson and many-body localized regime. Well, you see that it's getting a little bit sharper, right? This is log scale. It's getting sharper as you increase the system size. So this might hint that there might be a transition between the two and not a crossover. And then another thing you can verify is that as you increase disorder, ETH starts breaking down. And so here what you see is difference, right? Average difference of sigma z observable between two nearby eigenstates. So you expect, in light of what we discussed yesterday, in the thermalizing phase, you expect that ETH would hold and this difference would be very small. So it will get smaller and smaller as your system size gets larger, while in the MBL phase it would be all over the place because you have conserved quantities, right? And two nearby eigenstates can have a different local integral of motion. And therefore, right, and here you see that, so here different curves are different disorder values, and blue and green curves are for weak disorder, right? And you see indeed that this difference goes down very quickly as you increase the system size, while at strong disorder, essentially it stays constant and of order 1, right? So it tells you that ETH does not hold. And in general, so in particular for studying thermalization, actually, because Hilbert space dimension grows so quickly, you can see ETH very nicely already, at these relatively small system sizes. So, okay, any questions about this? Yeah. Yes, people have done various versions of finite size scalings, trying to extract critical exponents, but I think the conclusion is in general that these system sizes are too small to really gain an insight into, properties of the critical point, right? Because depending on how you do things, you really arrive at different results, and which is not, ultimately it's not surprising, right? Because here you have, this is system size 20, right? You cannot be expect to sort of hit universal physics with your transition yet. At the same time, in terms of numerical studies here, you're very limited, right? Because more or less there is a hard exponential wall you're hitting, and there isn't a clever trick, with quantum Monte Carlo or so to take you further. You can try to go from the many-body localized side with tensor networks and get a little bit further, right? But here you're really pretty constrained in terms of numerical studies. Right. So, but you would in general, in the studies of integrability breaking, you would see these types of plots quite a lot, whether you're talking about many-body localization or studying how integrability breaks down, right? For example, if you take a beta ansatz solvable chain and perturb it slightly, right, it is very common to look at level statistics. Okay, so then another thing we discussed was this logarithmic growth of entanglement, and here is an illustration, right? Illustration of how entanglement grows now in the many-body localized regime in a quantum quench as you add weak interaction to the system. So as we discussed, this we discussed yesterday, so this is just an illustration. So if you have no interaction, then you see in the Anderson localized regime, you see that entanglement grows a little bit when particles, hop across the boundary within localization length, then it saturates, nothing more is happening. And then if you turn on even very weak interaction, right, you see that there is this logarithmic growth of entanglement. So this is log of time on the x-axis, right, which proceeds for many decades in time, and that's okay. That we understood yesterday in terms of this idea of local integrals of motion. Right, so that idea of integrals of motion we have discussed, so I will just flip through it. And dynamical properties of many-body localization, right, this idea of having that once you have integrals of motion, you can go to the, right, and write your Hamiltonian in terms of this conserved quantities. Yeah. Yeah, sure. Mm-hmm. Right. Mm-hmm. Mm-hmm. Well, I would say the simple argument you have, it comes from here, right? Because you can think of this phase as a bunch of qubits which can dephase each other, but their interactions decay exponentially in space, right? So you only feel this qubit there after a time which is inverse of the interaction, right? So it is exponentially long in distance, right? So you get time, right? Time going as e to the x, right? And therefore x going as log t. So that's a simple intuition, and it's pretty much allows you to understand what happens. Right, but this also tells you, going back to thermalization to something like Lieb-Robinson bound, it tells you that here information would spread a lot slower, right? So you are very far from saturating Lieb-Robinson bound, for example, in some sense. While in generic systems, operators grow, there is a linear front, right? And this is really the consequence of strong disorder and having these conserved quantities, which greatly restrict your evolution. Okay, any other questions? Yeah. Okay, so then another illustration I wanted to show to you. So we could appreciate the importance of matrix elements, right? And this picture that is sometimes, quite intuitive and useful of when you perturb your system, right? Then thinking about a hopping problem, right? Hopping problem in the basis of original unperturbed eigenstates, right? And this is something again that came up, but we can ask, so how does a local perturbation affect eigenstates in the thermalizing phase versus many-body localized phase? And one natural measure you can introduce, you can say, well, let me add a local perturbation here, and then look at the matrix elements, at the statistics of matrix elements between the original eigenstates. And then our expectation is quite different, right? That in the thermalizing phase, we expect matrix element to go as 1 over square root of the Hilbert space dimension, right? That comes from the ETH ansatz, while level spacing goes as 1 over Hilbert space dimension, so it goes as, so delta of L is level spacing, goes as 2 to the power minus L. So matrix element is much greater, you expect to see lots of resonances and your eigenstates would be strongly modified. So in the delocalized phase, this hopping problem looks a little bit like a random matrix, right? Particular random matrix, which is random over some interval of energies. While in the localized phase, you expect that a local perturbation, right? That a local perturbation, because you have your conserved tau spins, right? And you expect that truly local perturbation becomes quasi-local in terms of tau spins, right? So it can only flip a few spins in the vicinity, right? Within localization length. And therefore, here you expect, you expect these matrix elements to be very small, right? There are only a few large ones. They have a broad log normal distribution, right? Because effectively they come as, products of random small numbers. And that's your expectation, right? And you can ask, okay, so what exactly happens to the matrix elements at the transition between the two phases? And so here is the illustration. So in the thermal phase, and we can characterize what happens by this parameter, which is a little bit motivated by the Taulis parameter in single particle localization, which is I'm gonna average log, right? Log of the ratio of matrix element between two nearby eigenstates and their energy difference. So why log? Well, because we'll be dealing with broad distributions, and I want to be looking at typical and not to be dominated by some tail, right? And then you can average this many-body Taulis parameter and see that, in some sense, if it's large, it tells you there would be lots of resonances, and you'll be very sensitive to local perturbations. If it is very small, then you don't really have resonances, and you are dealing with a stable eigenstate. So it tells you that your system is integrable in a rather, let's say, robust way. So, and here is what happens in the thermal phase. So you see that as you increase the system size, indeed the probability distribution of G gets shifted to the right, so it grows larger, you have lots of resonances, while in the MBL phase, it shifts to the left, right, and the distribution broadens, so you have fewer and fewer resonances. And then, one tentative criterion you could adopt for finding the transition points is to say this is a point where you have order one resonances, right? So somehow this value of many-body Taulis parameters stays roughly constant. This is what happens in single particle localization. But again, so so this is one of the approaches you could take, right? There are others, and then you can try to build a theory, let's say, which would incorporate this hypothesis. So now, let me just flash one slide about experiments on many-body localization. And here again, there is a lot more to it, but just to give you an idea of what people do with synthetic systems. So some of the first experiments, right, which really try to probe many-body localization, were done with ultra-cold atoms and optical lattices. And here, so what they realized in Munich, so they had two incommensurate lattice potentials, right, which effectively creates quasi-periodic, right, quasi-periodic potential, which looks disordered. It's not truly random, right? But for example, you would have localized eigenstates there at the single particle level. So it's a good starting point to look for many-body localization. And then, so with their capabilities, they can prepare initial states where they put atoms on even sides of the lattice, but not on the odd sides. And then you can see how this pattern, how this charge density wave pattern, whether it relaxes as your system evolves or not, right? And if it gets washed out, you conclude that your system is thermalizing, right? Of course, it does not imply that you are reaching thermal equilibrium, right? You need to do more to really show it, but it's a hint, right? It's a good indication. And then if it stays, if this pattern persists, right? You say that okay, system has a hard time exploring the full space of configurations, right? And this is indicative of many-body localization, because this would be, what we know is that this, for example, density on this site would have an overlap with one of our tau operators, and it's conserved, and therefore, right, that's how the system retains memory of initial state. And here is the phase diagram. Of course, with the caveat that these experiments can run up to some finite time, maybe long but finite time, before undesired decoherence destroys your system, right? So it's always done at finite time, and I think this would always be like that, right? That you would have to be at least in a quantum quench type experiment, right? So you make statements about behavior of your system at this long time you can reach. And here it's plotted as a function of interaction on the x-axis and strength of quasi-periodic potential on the y-axis, right? And then you see that at sufficiently strong quasi-periodic disorder, you enter presumably localized phase, right here. And then as you decrease disorder potential, then you become delocalized, and you see relaxation of this initial non-uniform pattern. These systems allow you to do quite a bit more. So people have also measured entanglement growth, right? Because they can actually go and measure, collect statistics on the configurations, right? On really microscopic configurations of atoms, and then estimate entanglement entropy this way and see this signature of many-body localization, which is log growth of entanglement. So any questions about this part? Okay, so then let me just touch upon a bit more about some difficult open questions, right? In particular, in terms of trying to build a theory of how many-body localization gets destroyed, right? And we can take this picture that we were discussing yesterday, that at first, at very strong disorder, you start by doing order by order perturbation theory, which takes into account locality, right? And then you find, these large chunks where perturbation theory worked and you didn't hit any resonance. And then, rarely you would hit a 2-spin resonance, and very rarely you would hit a 3-spin resonance, right? And those you have to deal with non-perturbatively, and you make a entangling unitary transformation on those spins. And these resonant regions are pretty rare, right? So finding finding a block of spins where disorders all happen to be roughly the same, of length L, so that's exponentially suppressed in L, right, with some prefactor A of W, which depends on your disorder, right? Essentially depends on the perturbative parameter J over W. But there is something that is, in this logic, so the danger is that if my block of spins happen to be a little bit larger, right, it can act as a small thermal bath, right? So what it can do, it can now thermalize in a way. Sure, it's a finite thermal bath, so it's not, it has a finite level spacing, but what it can now do, right, it can get entangled with spins in the localized block nearby, right? That's the danger. And sure, if your disorder is very strong and you can bound it, nice, but turns out that this is, so what you can do, you can bound the probability of this happening at very strong disorder, right? That's what Imbri's proof is trying to do, right? But then really, sort of as your disorder gets weaker, right, and this thermal inclusions would be for sure there, right? There is a question how they would interact with the localized regions. And there is a nice simplified model which was introduced, which actually showed something very interesting. And to model this situation, so what they did, they said, okay, so let us say that in this localized block, we have the description we discussed yesterday. So we have local integrals of motion, we have some tau operators. And then let's say that the small bath is a very good bath, so we can approximate as a small random matrix, right? And then, so what you can say, well, I have a bath, right? I have this thermal little blob, which I describe as random matrix. And then I have my Hamiltonian of the localized block, and I'll really treat it in a very simplified way, just by tau z operators, and even forget about tau z interactions we had. And then we will introduce some weak interaction between this thermal block and local integral of motion far away. For example, I would say that they can flip, right? So spin in the bath can flip, and our local integral of motion can flip with some amplitude that decays exponentially with the distance between the spin and the bath. And then you can follow the logic using Eigenstein thermalization, and this estimates of having resonance, right? Having resonances, and you can ask, okay, so let me start with adding one spin. So would there be resonances? So for example, would the state n of the bath and state tau 1 of my spin hybridize, right? Can the spin flip? And to answer this question, so what I need to do is essentially look at the matrix element, which I can estimate from the ETH hypothesis for my small bath, right? So I would say, well, it goes as 1 over square root d, level spacing is 1 over d, so there would be typically a resonance. So I can absorb one spin. And then it means that in the eigenstates, this bath and the initially localized spin would get entangled, right? So it becomes part of the bath. And therefore the bath grows, right? And its level spacing decreases. And you can continue this logic, right? And argue that despite the fact that you're absorbing localized spins, actually matrix elements tend to remain ETH-like, right? And then you can continue this and see that after essentially, after our steps of this procedure, your bath has grown quite a bit. Now the Hilbert space dimension is 2 to the power r times original dimension of your bath, right? But the coupling decays exponentially, right? And then you can see that probability of absorbing the next spin goes as e to the minus r, right? 1 over zeta, where this is how fast your coupling falls off, and then this factor of log 2 over 2, which comes from the growth of the bath, right? And so therefore, if your interaction falls off sufficiently fast, this is not dangerous, right? This will stop. But if not, this would become an avalanche, right? So this small bath would slowly absorb, right? Slowly absorb all your localized spins. Of course, this is a model, right? There are things which are not in it, but it's a pretty interesting mechanism, right? And you can imagine that this would be relevant to some models. Yeah. That's right. Yeah. Mm-hmm. No. It's not justified. So it's a. Mm-hmm. I think this is one strong assumption here, right? That you need to get a very good small bath, and if you take a spin chain with disorder, you don't really get that, right? I mean, okay, you would get it extremely rarely, and if this block is sufficiently large, but this is extremely rare, right? So ultimately, you would find that this at strong disorder, this would not really affect your experimental results, right? Just because the thermal inclusions are so rare. Yeah, that's the right point. But from this point of view of really, really very long times and really asking about stability of MBL phase, so this is of course relevant. But then what is even more curious, that if you go to higher dimensions, then you find that if I go to d dimensions, right, I find that my bath grows very fast, right? It grows as 2 to the power r to power d, right? So for example, in 2 dimensions, this would be 2 to the power r squared, while the interaction falls off only exponentially. So you would say, well, this always wins, right? So my bath, there would always be an avalanche, right? Of course, again, in practice, to get an avalanche, you'll need a very large thermal inclusion, which is a sufficiently good thermal bath, and this could lead to some process at scale of 10 to the 10 or something, right? Which in practice you can safely ignore. So, but still, you see that, right? In terms of really building a theory, you have to deal with this question, which is somehow turns out to be a difficult question of how a thermal bath interacts with a localized region, right? And along the way, it becomes a bath which is, somehow not so good, and yeah, we just don't have right tools to describe that right now. That here we said that essentially this bath was a random matrix, right, and not a system of spins with local interactions. Yes. Right, exactly. Yeah. If it is exponentially slow or exponentially small? Well, right, I think that's exactly the point of their argument, right? That if you take a very large system, somewhere there would be a good bath, right? And it will, but if density of such good bath is exceedingly small, right, then time that it would take for a typical spin to thermalize by such a bath is still exponentially small in the distance to the bath, right? So you would never see it, right? So, I mean, what I think what would be very nice to have is realistic estimate, right, of how frequently you encounter sufficiently strong thermal inclusion, and yeah, what estimate on thermalization timescale this would produce, right? And you know, my feeling is that you would end up with a strong disorder with timescale which are really astronomically long. Right, and for that reason, you see also an experiment, right, that phenomenology of what we discussed, MBL holds even in 2 dimensions, even though, you know, this argument suggests that eventually, you know, at very, very long times, right, system might thermalize on its own, sort of on its own. But here you see, this other experiment now in 2 dimensions, right? Atoms in a disordered lattice in 2 dimensions, also from the Munich group. So you vary, right? You vary strength of disorder, delta, and then you, right? Then you can see how atoms which are initially loaded in half, right, in left part of the lattice, right? How they spread throughout, right? Throughout here, or you know, in the localized phase, they stay, right? They stay stuck where they started, right? So you can study this phenomena, but you are limited, right? You are limited in the times you can probe, and presumably those times are shorter, right? Or likely much shorter than these timescales for thermal avalanches, right? And that's okay. That's challenging, and yeah, there is room for some clever idea. So okay, any questions about this? Okay, yeah, I guess skip that. So let me just mention one last thing about MBL. So one nice application of many-body localization has been for driven systems, right? And people, you know, there are many reasons to study driven systems where you modulate Hamiltonian in time, right, with some period t. So in this case, you don't have, right, you don't have energy conservation, so you have to instead consider Floquet operator, right, which is evolution operator over one period, and then you can think of your evolution as, you know, applying this Floquet operator over and over again, right? And you know, people have been using this idea of driving to engineer effective Hamiltonian of your system, right? And try to, for example, find driving which would lead somehow to a better control of your many-body system. And you know, naively you could say, well, if I could write an effective Hamiltonian, and formally I could do it, right, and write the Floquet operators as an exponential of some effective Hamiltonian, then, you know, I'm trying to find a driving which would give me a desired H effective. But of course, there is a, right, in a many-body system, when you shake it, there is heating, right? You expect generically heating, and that makes, in general, this H effective, strictly speaking, non-physical, right? Because ultimately you don't have energy conservation, so you cannot have a physical conserved Hamiltonian, right? And this is where MBL leads to something interesting, because actually turns out that there is a regime where driven many-body localized systems do not heat up, right? And this is intuitive because, you know, you can think of, right? You can think of, you know, shaking MBL system, right? So you are trying to absorb photon from your driving field, right? You need to find a resonance, right? You need to find a rearrangement of your conserved quantities which would exactly match this energy. But as we somehow essence of localization is that there are no resonances, right? And locally you can only couple to processes of flipping, one or a couple of spins here, right? So there is a finite number of such processes, right? And energy changes would be likely off resonance compared to your driving field, right? Then, of course, to really convince yourself that the system does not heat up, you have to account for processes where a few electrons or this, tau operators far away reshuffle, trying to match the energy of the photon, estimate matrix element, but then you can, argue that this also stays off resonant, and therefore, essentially, this integrability can persist even with driving. And this led to some interesting ideas, right? That there are different phases, distinct phases of driven many-body localized systems. And okay, without going into details, maybe you've heard about this idea of a time crystal, right? Where you can have persistent oscillations at half the driving period, and this is all built on this idea that many-body localization of loci systems right, can persist, and you have no heating. So this is just to mention one application. There are some other interesting applications. So for example, in higher dimensions and periodically driven systems, you can have some new topological invariants. For example, you can have chiral edge states at high temperatures and excited states. So it's a little bit like quantum Hall effect, but has quite a different origin and different topological invariant. So, and with that, so let us maybe make a break here. But first, any questions? So here I'm going a little bit fast, but I just want to make a connection between different things you would see in the field, right, and what we discussed. Yeah. What is known? Well, I think in one dimension there are theories which build some kind of phenomenological RG, right? By coming up with rules of how you should merge thermal and localized blocks, right? And then then you end up with some predictions for critical exponents and things like that. But I would say the question is how justified these rules are, right? Because ultimately you are dealing with a situation where you have a localized block and a thermal block, and then you have to declare that together they become either localized or thermal, right? And that's the part that is is being discussed. Then you can try to incorporate these types of avalanches in the picture, and people have done that, but still I think there is no real consensus whether this is enough, right? Yeah. Where in no heating property? Well, it's I mean, in general, interacting system would be more susceptible to heating, right? Yeah. Right. So what's surprising? Yeah. Yeah. So they would not heat up. They would not heat up. Right. Exactly. Yeah. It's harder. Right. Exactly. Right. Mm-hmm. That's a very good point. So indeed, there people have been interested in this idea whether you can get quasi-MBL-like behavior from just interaction, right? And indeed, so there are you can imagine that indeed if you have very strong interaction, right, then typical configuration would look kind of distorted, right? Because so what you need to engineer is a situation where starting from some generic state, right, any move you're trying to make is kind of blocked because it's off resonant. And people have done that, but then once again, you run back into this question of, okay, so there would be configurations which are translationally related by translation. They must have the same energy, whether those resonances destroy it or not, right? But yeah, there are interesting works in that direction, so that's yeah, that's an interesting, certainly interesting idea to explore. And there is no doubt that you can get very slow dynamics from from strong interactions, from constraints and so on. Maybe let me just make another small comment. So, we've been talking about avoiding thermalization, ergodicity breaking. Of course, another broad class of phenomena we are not touching where you would hear ergodicity breaking are glasses, right, and spin glasses, right? So MBL is very different from spin glasses, right? Because here, really MBL is based on this idea of localization. So, elementary moves are blocked because spectrum is discrete, right? And energies are incommensurate, while glasses are largely, this is a classical phenomenon, right? And it comes from frustration, right? From the fact that essentially you start getting very different configurations at low energies, which are separated by large energy barriers, right? And so your phase space breaks into this kind of disconnected parts, which are, takes a very long time to traverse, right? But generally within one, let's say one of this minima, right? There you would thermalize, right? It's just your phase space breaks into disconnected parts. Now, you can ask now, going to quantum systems, what happens if you combine frustration and strong disorder and try to get MBL, right? And that's interesting. And well, in general, of course, having frustration would help, and going to low energy, where glassiness becomes relevant, typically, right? It would help MBL as well, just because you have fewer options to hybridize with other states. Right, shall we go for a break? I was worried. I thought you guys trashed the hotel and had a huge party yesterday. But so okay, so let's continue. And first, any questions already now? Okay, so yeah, I imagine you must be completely exhausted. But so now let us discuss a little bit what we find, which is beyond many-body localization and thermalization. And here, if we really compare side by side the properties of ergodic and many-body localized phases, you see that they're really on the opposite ends of the spectrum, right? Because eigenstates of ergodic systems are in a way maximally entangled given the constraints of energy conservation and so on, while many-body localized eigenstates have very little entanglement, area law entanglement, right? You have, in terms of conserved quantities, you have only global conservation laws, like energy, for example, on the thermalizing side, and you have essentially one integral of motion per degree of freedom in the MBL phase. And same goes for spreading of correlations, right? So they're very, very, very different. And so, and it's really, a natural question to ask whether we can find phases or at least regimes, right? More regimes with some intermediate properties. And in particular, can we have different entanglement patterns in eigenstates, right, in terms of dynamics? And here, so there is a couple of routes you can pursue to answer this question. And so, and one interesting direction, which I will not elaborate on, is adding symmetries to your disordered systems. And so, in particular, if you have, turns out that if you have non-abelian symmetries, such as, for example, SU2 rotational symmetry, this is not consistent with usual MBL as we discussed it. Turns out that non-abelian symmetry would give you a lower bound on the entanglement of eigenstates, right? So eigenstates must have at least log L entanglement, right? Which is a bit more than area law that we see in MBL. And this, this ultimately arises because if you have a non-abelian symmetry, you know that eigenstates would come in multiplets, right? So there is this degeneracy dictated by symmetry, and that gives you a bit more room for resonances. And then, okay, you can. So it's still, I think, there is a lot that's not understood about the systems, but it is suggestive that there is at least a broad regime which is non-ergodic and different from MBL, right? As we learned it. And then there are two other possibilities which I would like to mention a little bit more. So, and one is quantum many-body scars, right? And that's a fun example because it came really as an experimental surprise. And here you see that your system is generally thermalizing and satisfies ETH, but there are some outlier, right? Some outlier states which are special, which have low entanglement, and then if you start an initial state which has an overlap with those states, then you see, you can see very slow thermalization or no thermalization at all. And then another option is pre-thermalization, right, which we already discussed a little bit. And there are different types of pre-thermalization, in particular, what happens if you take a beta ansatz integrable spin chain and break integrability, right? How does GG get destroyed? How do different integrals of motion get destroyed? But I will be interested in a slightly different type of pre-thermalization, which does not rely on initial integrability, but rather it just requires that there are two different energy scales in your problem. For example, you have a Hubbard model with very strong interaction, right? And turns out that in this case, right, you are guaranteed to have an approximate integral of motion which would be very long-lived, right? And this is also a nice example because, here you can derive some rigorous results and really make those bounds rigorous. And so maybe and here, I'm not sure we'll have time for both scars and pre-thermalization, really to go a bit in depth. So here maybe I can ask you what you're more curious about, and then I'll start from that. So scars, yeah. Okay, so let's do scars, since that's one one preference I heard, unless there are objections. So, but then what I will do, I will just formulate idea of pre-thermalization on one slide, and then I'll go to scars. I think this is a good plan, given that you already covered a lot of very different things during these 2 weeks. So I think we can focus on scars. But so idea of this type of pre-thermalization, right, is ultimately very simple. So, and you can see two sort of manifestations of it in two physical situations. So first, where I think it came up really first clearly was in periodically driven systems. And so, and here I emphasize that now I'm not considering disorder, right? There might be disorder, but I don't, I'm not going to rely on disorder. So this is quite different from MBL. And for example, let me consider some latest model of fermions, for example, with periodic driving, right? So I can imagine, as they do an experiment, modulating hopping or modulating interaction in this case at some driving frequency omega, right? And the fact is that if you are in the regime where driving frequency is much larger than your interaction scales, right? So in particular here it would mean that omega is much greater than time-dependent hopping and time-dependent interaction, right? Your local energy scales, then the system would generally heat up, but you can bound this heating, right? You can bound this heating to have a rate that is exponentially small in driving frequency over the local interaction scale. Right. And in this case, you can say more. So you can actually say that in this limit, dynamics up to this heating time would be well approximated by an effective Hamiltonian, effective static Hamiltonian, which is consistent, right? So you have, in this case, this effective Hamiltonian, it becomes an approximate integral of motion, which moreover governs your evolution, right? And then after, so degree of its non-conservation is small, right? Exponentially small in omega. So after time omega, okay, it just decays. Right. Yeah. Hermitian. Yeah. Right. I mean, here, the key property here is really that it is difficult, right? It is difficult, for example, if you have a spin system, right? And each spin has energy J, and you are trying to dump much larger energy into the spin system, right? So if omega is much greater than J, then to absorb a photon, you need to flip many spins, right? And despite the fact that you don't have disorder, right? So you can bound all these processes, and there is a nice, sort of application of tools of quantum information, in particular, Lieb-Robinson bounds you have to use to get there, right? So it's, but that's the intuition, right? That for a system, it's difficult to absorb a lot of energy at once. So that's a slow process. And another another facet of the same phenomenon arises in static models. So for example, if I have a Hubbard model here, right, actually in any number of dimensions, and if I'm in large U limit, right, so interactions is much stronger than hopping, then number of doublons, number of double occupancies which give you energy U would be approximately conserved up to a time, right, up to a time which is exponentially long this time in U over J, right? So once again, it is difficult to decay a doublon. You have to give energy U to your spin waves, right? And that's difficult. So that's the idea, right? And so you see that this would be a very, very general mechanism for having approximate conservation laws, right? And indeed, there are various nice applications that people have found. So in particular, for example, Paul Fendley found some very nice connections of this to long-lived edge modes, right? And those you can also observe experimentally. So yeah, and that's what I'm going to say about pre-thermalization. Where does exponential come from? Well, so let's think about it very, very naively and imprecisely, right? So so you can think of absorbing a photon that you need to somehow go to a high order. Okay, so maybe let me do it like that. So let's say I'm thinking about fermions, right? So I have their band, right? Their energy dispersion, and let me make these fermions weakly interacting. So let me say that I have that Hamiltonian, right? But V is small, right? Then, so I'm dealing with some, some occupation of this band, and the bandwidth is of order J. Then to absorb large energy omega, so what I would need to do, I would need to reshuffle a lot of these levels, right? I will need to, for example, put this guy here and this guy there, right? So I'll need to essentially consider number of shuffles, which is of order omega over J. And now in the limit where v is small, right, the only way I can do it is by invoking interaction. So this would be a process of order n in interaction, right? So that's how you would get that this would be, this rate would be very roughly, right, would be v to power n. So it would be something like that, right? And v is small, right? So here is how you get a small exponential, right? Something exponentially small in omega. Now, you can make it much nicer and actually not relying on weak interactions, right? Using the tricks related to locality and Lieb-Robinson bounds and so on. So, okay, any other questions? So, okay, so then let me go to scars. And here, so as I said, so what was very nice about it is really it was an experimental surprise, right? And it came with the sort of first wave of recent advances with Rydberg atom arrays. And this was an experiment, right? This was an experiment from Harvard-MIT collaboration. So, and what they did there is this controllable Rydberg atom arrays. And in this particular experiment, so this was a one-dimensional array. And what these Rydberg atoms are like. So effectively, you are working with the ground state of the atom and also some highly excited Rydberg state, right? Meaning it's some orbital, 70s or something like that. So it's huge, right? Electronic state is really huge. And what is nice about it is that you can, if you bring two atoms sufficiently close by, right, then both of them cannot be in Rydberg state simultaneously because their orbitals would overlap. It would cost too much Coulomb energy, right? And therefore, you can tune this arrays in the regime of Rydberg blockade. So where essentially, so let me denote ground state by an empty circle and Rydberg state by a black dot, right? And you can be in the regime where effectively your dynamics is constrained. So you can have Rydberg excitations, right, but not two of them next to each other. And then this is a driven system, right? So you're constantly shining a field to couple ground and Rydberg states. So effectively you're Hamiltonian, right? It keeps flipping in the rotating frame. It just keeps flipping between ground state and Rydberg state. So that's, I just have sum over xi where x is a x Pauli operator on spin I acting in the space of, this two-dimensional space of ground and Rydberg state. Plus I have the constraint of Rydberg blockade, right? So I'm not allowed to create two of them nearby. And what they saw, so then they, went and studied quench dynamics for different initial states. And they saw that this type of a state where you had a maximum possible density of Rydberg excitations, right? So where you had a Rydberg state on every other side, was actually long-lived, right? And it showed some some observables, like in this case, domain wall density, showed long-lived oscillations, right? And somehow this hinted that such a state does not thermalize in a simple way, right? And instead, there is a sort of many-body revival that your wave function finds its way back in the sludge Hilbert space. And this was already a pretty large system, right, of about 50 atoms. So, it is quite non-trivial that some initial states would come back. And what was even more striking is that, for other initial states, for example, if you start with all states 0, right, all ground states, then you would see sort of plain vanilla thermalization, quick relaxation to thermal ensemble. Therefore, you can see already that this is very much unlike many-body localization, where you don't expect thermalization for any initial condition. And then so this model actually turned out to be quite interesting, So I can write the Hamiltonian in such a way that constraint is incorporated already in the Hamiltonian, right? So I can say that my Hamiltonian is an X operator dressed by two projectors on the left and on the right on the ground state of my neighbors, right? So I can only flip if my neighbors are both in the ground state. So this is a, with this constraint, your Hilbert space has no simple tensor product structure, right? And its dimension goes as essentially Fibonacci number. That's something you can easily derive with, simple transfer matrix. And you can start by thinking about hopping problem, the space of states that this Hamiltonian defines. It has a lot of structure, a lot of symmetry. It's some nice graph that you live on. And then, to further convince yourself that this is unusual and interesting, you can go and study level statistics, right? Level statistics of this model. And what you discover is that actually level statistics is, there is level repulsion. So here I'm plotting probability distribution of level spacings, right? Properly normalized. So you see that it goes to 0 at 0 level spacing. So that's level repulsion, right? Wigner-Dyson statistics, and then it drifts towards really Wigner-Dyson distribution. So, so it's very far from the Poisson distribution. Then, furthermore, entanglement for usual, let's say, usual initial states grows linearly. So just as you would expect in a thermalizing system. And then, to get a first sort of insight into what is happening, what these revivals are from. So what is quite instructive is to study entanglement entropy of the eigenstates. Right. So and here, so I'm plotting entanglement entropy for cutting system into two halves, right? For all the eigenstates of my model, arranged by their eigenenergy. Right, and you see that really the vast majority of states are following this inverted parabola, and that's what you expect. That's just thermodynamic entropy, actually. But here you see, and typically, right, if you have a ETH system that satisfies ETH, more or less all your states follow this parabola, right, with very little deviation. But you see that this model is not like that. So in fact, in particular, you see this band of states, right, which have very low entanglement, which are separated from the bulk, right, from the bulk of eigenstates, which are thermal, right? So states which are in this parabola, they're thermal essentially. But these ones are not, so they're somehow special. And turns out that these special low entanglement states, which you find throughout your band, actually have a high overlap with this Néel type initial state, which I'm calling Z2, right? That's the state where I have Rydberg atom on every other side. So if I'm now plotting weight of the two states on different eigenstates, so you find that it has a lot of weight on this special band of states. Right? While of course, if I had a normal thermalizing system, I would not see anything like that, right? It would be just some Gaussian distribution of weights. And so it's an interesting question. How does this band come about? Right? Can we understand it algebraically, in particular, and what is the underlying structure? And to construct it, right? So one observation you can make, you can say, well, let me actually. So the fact, right? The fact that these states are equally spaced in energy hints that there is some nice algebraic structure behind them. And the fact that you have revivals also hints that there is some kind of large spin dynamics going on. Yeah, that's right, that's right. Mm. Well, so here actually, yeah, that's a little bit, that's curious. So here, I think here you are dominated by these anomalous states, right? While here, you're dominated by the bulk of thermal states. So these thermal states on this plot, they're all here, right? They're all, this is just a blob, so, right? But yes, you're right that if you were to plot it, I think, if you were to plot it for a sort of normal state and really see where most of the weight sits, it would follow density of states essentially. Yeah, because it comes from density of states. Yeah, good point. Okay, any other questions? And to construct, right, to highlight this underlying structure, so what you can try to do, so you can try to break your Hamiltonian into two parts, which would be like a raising and lowering operator for a large spin. And clearly, since we expect that Néel state 0, 1, 0, 1, 0, 1 would be like a largest SZ state of this fictitious large spin. So the way I want to define them, I want to define raising operators on the even sides, right, and lowering operators on the odd sides, such that Néel state would be annihilated in this case by H minus. Right. And then I can play with the algebra of these operators. And so what you find that in the first order, as you commute them, it starts looking like a Z, right? Difference of the Z projections, of course, dressed with P's. Right, so okay, so that's good. That looks like a large spin. Naturally, this is a many-body model which is thermalizing, so it cannot stay like that at higher orders. So if I compute next correlator, next commutator, I find that there is a correction which is less local, right? But it looks like that. So it's dressed now by two projectors, and there is a spin flip. So, but still, you see that this smells a little bit like a spin algebra. And the idea is that, right, this algebra does not hold on your whole Hilbert space, but it holds pretty well. It closes pretty well on this subset of states. Right, so, and then so to get the first feel of whether this is really what's going on, so you can consider this subset of states of large spin states that you would generate by acting with raising operator on your Néel state, and then find the spectrum, right? Find the spectrum of just this in this projected space. And what you find actually that this gives you a pretty good approximation. So you get already eigenstate energies within 1%, and right, you can see that the structure, right, how this wave functions look like are actually captures reality pretty well. So this is the first hint that there is an SQ2 algebra which closes on the scar, right, subset of states. Of course, it doesn't tell you why is it emerging, right, from this model, whether there is a solvable point, and I will comment on that a little bit in a second. But first, so let me explain why they were called quantum many-body scars, and then you can judge for yourself whether it's a fair name. But now I think the name stuck, so there is nothing we can do about it, right? But the way it emerged, right, is from this analogy with few-body chaos, because so going back to the stadium billiard, where as we said, classical motion is chaotic, and then you can ask, if I put a quantum particle in the stadium billiard, okay, I expect most of wave function to be kind of ergodic and featureless. But turns out that there is a subset of eigenstates of measure 0 which do not look ergodic, right? Which are structured. And these have a curious origin. They're actually related to periodic unstable classical trajectories, classical orbits. So for example, in this billiard, I can find a trajectory which bounces like that, right? Of course, it's unstable, so if I, and it's a chaotic system, so if I deviate a little bit, then with Lyapunov exponent, I would exponentially diverge, right, from it and run away, or I have this type of bow tie trajectory. And turns out that you find quantum eigenfunctions which carry the structure, right, which remember the structure. And these are called quantum scars. And they occur if the Lyapunov exponent is sufficiently small, such that your particle can bounce long enough time on this trajectory, right? And you can imagine quantizing it, right? And this would have some implication for the density of states, right? It's a sort of a very famous phenomenon in few-body chaos, right? Which people studied in quantum dots and other systems, and you see that what we observed in this model is a little bit like that, right? There is a small set of wave functions which do not behave like ergodic wave functions. Specifically, this type of large spin construction would give me order L states, right? In this case, it's L states which are anomalous, but they live in the background of 2 to the power L states which are thermalizing, right? And then so you can ask, well, can we try to explore this link further, and can we use it somehow to make predictions or at least guesses for models which would have scars? And here where tensor network technology comes in very handy, because what you can say, well, this type of states which undergo revivals, right, they would not be super entangled. So what we can do, we can say, well, let us study dynamics of our many-body model projected onto the manifold of states with low entanglement. So meaning we would consider, for example, matrix product states with a given bond dimension, right? So bond dimension exactly parameterizes how much entanglement I can have, so I can controllably tune it and project my dynamics on that manifold. And then if you do that for this model of Rydberg atoms with matrix product states, with just bond dimension 2, so you find that actually you have a periodic trajectory which exactly represents this observed revivals. Of course, bond dimension 2 is very low, so you cannot even get chaos in this case. So, but things get more interesting if you consider larger manifold. And so in here, it is the same model, but now ansatz with 3-side unit cell, and so you have more parameters, and then you can plot the phase space of this variational dynamics on the MPS manifold. And here you see now chaotic regions and also regular regions, right? And where you see regular regions, right, that's your candidate for a many-body scar. And indeed, by studying this phase portrait, so you can identify some other states which thermalize anomalously. So for example, the 3 initial state where you have 0, 0, 1, 0, 0, 1, right? That turns out to have anomalous thermalization related to some other set of scar states. And this gives you an interesting connection between variational quantum many-body dynamics and classical chaos, and at least gives you, a possible route. Yeah. Andrea. Well, so here, this is a slightly peculiar thing, right? So here I'm projecting, I don't have a quasi-classical limit, right? Because I'm dealing with spins 1/2. So I'm projecting dynamics onto a manifold of states with low entanglement, right? So it's a slightly, yeah, I'm coming from a different limit, sort of, right?
I guess it exists also in the classical case, but they're kind of measured zero effects, right? But I would say in the quantum case, they're more important.
Yeah, right. Because they would show up for physical initial conditions, right? So, and actually, yeah, they would have, probably it's because some physical initial states would have a large overlap with these anomalous states, right? That's why they show up, and that's why even experimentally people stumbled across them. Yeah, that's a good point. Thanks. All right. Any other questions, comments? So yeah, you can. Right, this is just an illustration, but this gives you a way. Again, this is not right. This is not theory. This is just way of looking for candidates for scars, which I think one way that we have. And then so you can go back to this question, right? Really, it's a little bit of an interesting situation. So you have a model that is thermalizing, so it's non-integrable, yet you have a subset of states, right, where there is a lot of algebraic structure, and you can, well, at least with a good approximation, not exactly, but find them. So natural question to ask is whether we can, right, perturb the model slightly and really make it exactly solvable, right? See that scars become exact. And you can start playing with it by adding a perturbation with one extra projector. And right, so it turns out that by considering more such perturbations which are less local, you can essentially arrive at the model where scars would become exact and these revivals would become exact. And strength of the perturbation as a function of range here is given, right, is given by the essentially some function of a golden ratio. Now, why this arises, right, we don't know. Yeah. Yes, yeah. Right, because sigma z is Hermitian and projectors are as well, right? So I don't flip the project. I mean, it's a projector on a site, right? So it's 1 minus z, and then sigma x is Hermitian. Yeah. So it seems like there should be some, some underlying structure which we are not seeing, right? But we know that the scars essentially, right, there is a solvable point in the vicinity where they're exact. And turns out that there is a whole class of models which show scars, and actually around the same time as people studied this PXP model, an experiment was done. So similar structure was found also in the AKLT model, right? AKLT spin model for excited states. That system is still not integrable, right? So it tells you, and since then many other examples have been found of such scar states, and having a C2 algebra that closes on scar manifold, right? That's one way to get them. So you can also, right? You can also go to higher dimensions. You can stabilize scars by driving and do various other things, right? So that's gives you another example of anomalous thermalization of or non-thermalization for a long time, right? Which complements many body localization, and sometimes this type of phenomenon is called weak ergodicity breaking, right? Just because clearly it violates normalization in a much weaker sense compared to MBL, for example. And I think this is right. This is a good place to conclude, right? So we discussed, right? We discussed how quantum many-body systems thermalized, introduced ETH, right? Then spent some time on many-body localization and discussing this underlying integrability structure, right? Difference in entanglement, and then right then finally we discussed that there are also other possibilities such as quantum many-body scars and pre-thermalization. And so in general, you know, this field it keeps developing and it's becoming also, you know, I would say in a sense closer and closer with quantum information, right? And this attempts to find interesting and useful tasks for quantum simulators and quantum processors, right? And also finding new ways to control non-equilibrium quantum matter. So there are, of course, and you know, of course, there are many exciting things that I couldn't mention. So in particular, people have been very interested in what happens to this dynamics if you add measurements, right? So for example, as your system evolves, so we mostly considered, you know, Hamiltonians, right, Floquet evolution, but you can also ask, well, but what would happen if I, for example, if my spin system is evolving and then from time to time I can measure it in different places. So whether entanglement would keep growing or not, right? And so yeah, so that's, you know, one interesting set of phenomena which we did not have time to cover. But yeah, thanks a lot for all the questions, and I guess now we have some more time for discussion. Very few. So there is a couple of papers, and I think they're interesting, right? I'm not sure if they really changed sort of our understanding of it, but yeah, I think I can give you those references. I think, yeah. For quantum scars, I would say less so because here, I mean, once you understand algebraic structure, right? That's, I mean, you can understand other, let's say, other entanglement measures, right? But they would not necessarily add some new insight. Well, chaos should refer to, yeah, right, to having a level spacing which is Wigner-Dyson, at least in the right, yeah. You mean in my slides or in general? Well, it's good to be careful in general, but I think in particular, you know, so it was referring to this fact that experiments operate on a finite time window, let's say, right? So you can all you can conclude is that, well, the system does not thermalize up to this time, right? And all the scalings are consistent with MBL, right? But it's just the fact that these experiments cannot answer questions about very long time scales. But as I said, I don't think it's such a limiting factor, right? So if this analogy holds for for a very long time, then you can apply it, you can use it, right? And that said, I mean, I think the problem of really answering what happens in the extremely long time limit, it's an interesting problem, right? Which would likely, one would need to use, take some different view on the problem and try to come up with a probably different way of proving it or disproving it, right? Just because dealing, I mean, I think this, what Imri tried to do, all the dealing with resonances and probabilistically bounding things, it's just very, very complicated, right? So you need some, and my personal hope is that there is this one approach based on influence functional, which we've been studying recently, and there you can do disorder averaging from the beginning. So you can study, right? You can study some objects which are disorder averaged, and to me this could be, for example, a nice route to explore to try to, maybe get some rigorous results about MBL. So you, yes, you have to take symmetries into account, right? So I would not be able to say something useful on the fly, but I know the paper where you can look it up, so I can give you a reference. But in general, if you have, especially if you have some conservation laws, then you expect that ETH would hold in a given sector, right? That's a sort of a naive answer.
Any other question?
Everybody's exhausted.